So, welcome everybody in the after lunch session. One thing is that in this session, that is, I essentially give you some insights about the variable selection, functional data analysis, all those issues. And in the morning session, all of you are learned a lot about the variable selection. And regarding functional data analysis, I had a few notes. This is one of them because nowadays it is a hot topic. So we have several notes available in the if you do Google. But at least personally, I have two notes directly. This is one of my friend's note on Irwan Chakraborty. He is in EPFL. And another note I have that I am not following, that is he is now student in Michigan State. Essentially, Professor Mahit is a PhD student possibly. His comprehensive is not done yet, but he was my my former student when I was a faculty in presidency as well. So I had Protim's note and Anirvan's note. I was little bit in a dilemma which note I will follow, but at the end, since Anirvan is more mathematical, that's why I just considered this note. I just chose this note. First of all, one thing I want to mention, yesterday when I discussed about the non-parametric regression, and we started with the non-parametric regression. I defined the estimator, and I discussed something about the density estimation, marginal density estimation, joint density estimation. They are properties. That what will be the under what conditions those estimators will be consistent, all those mathematical facts I have discussed, and at the end we ended at the with the Nadia-Watson estimator, and I didn't mention in the slide, but I discussed in the board that whenever you are thinking about the Nadia-Watson estimator, that estimator can be written as a local constant estimator. I wrote it in terms of the minimization problem, and I mentioned also that instead of the local constant, you can consider local linear, local polynomial. In that way also you can think about local constant. Local linear means what I said, that is least square estimator with some weight, and that weight is essentially the kernel function. In terms of the kernel function you can write. Now there are several issues at the beginning. If you can recall yesterday's lecture, at the beginning I mentioned, when I defined the model y equal to mx plus epsilon. So y equal to mx plus epsilon, I considered the way we derived, that is essentially x was real valued, epsilon is a dot, and y is also real valued. That was the model, and m is a mapping from some ab closed interval to say r. That was the mapping of the unknown function m. Now next question was that, before I'll go to functional data analysis little bit after 10 to 15 minutes. First I want to settle down that issue because there should be a continuation. In the morning we discussed about the variable selection, so we should be focused, we should not lose the focus. So suppose instead of the one variable, one covariates, and morning what Professor Mahiti discussed a lot of on that issue. Suppose we have p many covariates, y equal to m of x1, x2, xp plus epsilon. So what I am trying to say that I am just writing here, you will understand I think better. So
sir, it's not properly visible from here. Could you please write down on this side?
This side, okay. Just non-parametric regression model. I am not writing anything very extraordinary. So suppose this is my model. Yesterday I considered y equal to m of x plus epsilon. Now I am considering better to write capital, I think, since we are writing. Y equal to m of x1 comma x2 to xp plus epsilon. This is my model. Now in this model, suppose p is very large. Already you are familiar with this business. P is large, p is greater than or equal to n. At least you have heard a lot about it. So if p is large, then we want to do the variable selection. So what Professor Mahiti's philosophy is that we don't need to think about the non-parametric regression. The parametric regression will be good enough. Why? What he is saying that am of x1 x2 xp, it is belongs to a some interval, that means it is belongs to a some 0 1 whole to the power p, something like that. So this function can be written as a arbitrarily large polynomial and then do the variable selection, and that polynomial and linear model means it is linear with respect to the parameter. So any non-parametric regression problem you can think about is an approximation of the arbitrarily large polynomial regression. That is his bottom line of his philosophy. That's why he said again and again that the linear model solves everything. We don't need to think about the even non-parametric regression. Not exactly, he didn't use that word, but it was his philosophy. So in that case, suppose I don't want to go through in that, I don't want to follow that philosophy. My model is y equal to m of x1 x2 xp plus epsilon. Now I want to p is large. I am not saying p is greater than or equal to n, p is large. Suppose even if it is p is small and p is less than small n, that means suppose n equal to 500, p equal to 20. That also not a very good model. So in that case, instead of the 20, if you can reduce it to the based on 4 variable, that would be good enough rather than 20 variable. So in that case, how do that? Anyone has any idea? Instead of the non-parametric, instead of the doing all those principal component analysis, all those things, just I am saying that you have the unknown function relationship y equal to m of x1 x2 xp plus epsilon. Now I want to reduce the number, I want to do the variable selection, that is what I am saying. I want to do the screening, rather better to say I want to do the screening. How do you do that? One way you can think about, the way I was thinking, suppose first I am considering y and x1, that is my data, forget about x2 x3 xp. So y and x1 some unknown relationship is there, okay. Data is coming, data we have to keep it very, data is something like, our data is okay, x1p. This is my, okay, p variable. This is 1, okay, it should be coming out as a 1p, okay. So in that case it should be coming out as a xp2 x2p. Whatever the inference I will consider, this is my data, this is my y response and this is my x vector, this is second vector, realization, all those, this is my data. Based on data we have to do everything. I am telling that don't need to think about the xt to xp, just consider I have one dimensional data, y1 x1, y1 x11, y2 x21, yn xn1, that one. Suppose with the first component my relationship is that y equal to m1 x1, okay, this is the relationship, unknown relationship. With the second component my relationship is m2 x2, okay, that means with the second component my relationship, and this is equal to mp xp, unknown relationship. Now from the given data I can estimate that what is my m1, what is my m2, what is my mp. From the unknown data I am writing this side, okay, I can write in this side. So from the given data we can estimate m1 hat, mp hat, it depends on n, we should write n also, okay. this p many unknown function we can estimate. So we can calculate the variance of this estimator also for the given data sample variance. So compute variance of mi hat, I is running from 1 to p. Just I am calculating the variance. We can compute it. That the sample variance, at least there is no problem. You just compute the sample variance. Then I am considering that the suppose it is intuitive feeling. I didn't formulate it mathematically. Just my feeling is that if the variance is very close to 0, that means if variance is close to 0. Okay, so this is my variance, all those things, variance of m1 hat, variance of m2 hat, variance of mn hat, and if variance does not have any impact, if m1 had sorry, if x1 is not significant, if x1 is not significant, x1 is some constant, something like that, then variance of m1 is the relationship with the x1, so that variance should be equal to 0. So what I am trying to say that suppose y x1 does not have any significant, x1 does not, it is insignificant, that means the coefficient related to the x1 that is equal to 0 in the parametric regression. So in that case, that variance of m1 hat should be equal to very close to 0. So my algorithm is that I will check that the which variances among those p variances which are less than or equal to some specified numbers, very small specified number, say 0.5 or 1. That is another mathematical issue that how do I choose that threshold value. So I am just computing the p many variances. I am choosing that I am checking that the which of them are less than or equal to some specified number c, and which one of them are greater than or equal to some specified number c. Okay, and which variances are less than or equal to some small c, those variables I am considering as insignificant variables, and whose variances are greater than or equal to c, those variances I will consider, those variables I am considering as the significant variable. That is my very much preliminary idea about the variable selection in the non-parametric regression.
Isn't this quite similar to the idea of principal component analysis? In that
Essentially, instead of the variance, you are considering the lambda. Eigenvalues. That means eigenvalues are essentially the variance of the principal components, variance of the principal component. That is quite similar, but using the marginal regression function from the joint regression, I didn't see so many papers, so many works. So I think that is, in that sense, it is new. But of course, that connection is there, because essentially what he is trying to say that whenever I am doing the way Sarvajit wants to point out that the variance is less than or equal to c means some sort of I am ordering. In the principal component analysis also we do so that we calculate the principal components, we calculate essentially principal components, we make the decision based on their variance, and that variance is essentially nothing but the eigenvalues. So essentially the same technique, but definitely the procedures are alada, different statistical procedure. So that way you can think about, the how to make the variable selection. I should not say, I would say that the screening of the covariates from these multivariate cases. That's why I had thought once, but I didn't write any paper based on this. But it is my very preliminary thought that this can be done. One way you can think about that variable selection, because you have learned a lot about the variable selection, AIC criterion, BIC criterion, all those things, and Professor Maiti Taps also discussed a lot. So that's why I thought that I can share my idea also, that this is my preliminary idea. So this section, the title of this section is that foundation of the functional data. So the way I generally think about the functional data, I am telling you, my thought is very straightforward, that I know what is random variable, x1, x2, xn, random variable I know. I know what is random vector, x1 curl, x2 curl, xn curl, that I know. To me, functional data means stochastic process. So suppose instead of the, so one step more generalization than the random vector. So x1, x2, xn is a random variable, sequence of random variables, that will give you the scalar. At the end of the day, if you fixed omega, x1 omega or x, what is random variable? Random variable is nothing but the mapping from omega to real line. If you fix 1 omega, you will have the one real number. That is clear cut idea in the random variable. Don't need to think about all those sigma field, all those things, mathematical deep issues. Next, random vector omega to rk. So if you fixed one small omega 1 belongs to capital omega, you will get back to the k dimensional number, the ordered vector. And in the case of stochastic process, if you fix 1 omega, you will get back to a one function for a different values of t. So instead of the at least one type of functional data, mathematically I can think about the sequence of the stochastic process. I am fixing the omega, I am getting back one function. That's all. So this is stochastic process. So in order to know the definitely there is I think one I need to be very specified mathematically. One fact is that functional space, functional data and infinite dimensional data both are not same. That's I would like to say. Infinite dimensional data, even a small L2 space, sequence data, that is also infinite dimensional space. Suppose a sequence data, ATCG, protein, all those things. This is all sequence data. So these are also infinite dimensional, but that is not functional data. So functional data is also infinite dimensional data, but I don't want to say both are same. To me, at least it depends on the perception. To me, high dimensional data, functional data, infinite dimensional data, both have separate names, both have separate concepts. High dimensional data means it may not be functional, but p is greater than or equal to something n, p has some order of n. So that is high dimensional data, but high dimensional data may not have the functional structure. For example, high dimensional data is observed at a fixed point, T1, T2, T3, T4, T5, T6, T7, might be n is 2, but that T1, T2, T3, T4, T5, T6, to me it is fixed. But whenever I am thinking about the functional data, that means I am observing the data in an arbitrary point. My T1, T2, T3 is not a fixed one. Otherwise, whenever you are thinking about the functional data, you can think about it as a multivariate data. There is no harm about that. Functional data speciality is that in arbitrary point you can observe. That is the only thing you can think about the functional data. But otherwise, if you fix the grid points, whatever the number of grid points, it is high or large, that maybe you can think about high dimensional data, or you can think about usual multivariate data. So I saw a few articles that the functional data means it is a multivariate data, make the dimension tends to infinity. Okay. There are a lot of theoretical paper I have seen that they are considering this is the functional data. To me, it is not functional data. It is not like that high dimensional data make d tends to infinity. It is not functional data. I would say that is a high dimensional data. At most I can say in that way, but I don't want to say functional data. So functional data means whenever each sample, each observation is a function. To me, it is straightforward. It is a straightforward issue. For example, curves or surface, it is called functional data. All those things. These are atoms of FDA, and this is growth curves of boys and girls, or temperature curves over a year for various weather stations. There are several examples. There is a very well-known book that Ramsey and Silverman, they have two books. One book is very much applied. You can think about that book. Essentially, these examples are all taken from this that book, Silverman and Ramsey book. Now, a little bit complicated you can make. For example, functional time series data. Just try to think about. I just want to give the one example. Whenever you are doing, we have here say 3 to 5, 1, 6, 7 or 8. We are about 7 or 8 people. We are doing our ECG for 2 minutes, or the length of 2 minutes, 120 seconds. So 8 ECG curve we have. This is functional data. So this is a one curve. This is a functional data. There is no problem with that. Now we want to what Professor Maiti also mentioned. Yesterday or day before yesterday, he was saying about the brain imaging data. That day before yesterday, at the very beginning. Suppose day before yesterday, what he is saying that brain imaging data. So there are some networks in your heads, and over the time it is moving. So that means a object is moving, an object is moving 64 components, 64 network channel is put in your head and it is moving over the time. So this is also a functional data, but you can think about that is a functional time series data. That means he didn't want to mention the time series, but I would say it is a functional time series data in the sense of this is a p-dimensional vector. That means it is a p-dimensional vector and each component is a one function. Or I don't want to say functional time series may have some different definitions. So the way he described the brain imaging data, I am just saying that you can think about in that way. He didn't write the mathematical formulation. Suppose say brain image data. What my understanding about his talk, it is x curl, it is p-dimensional vector, okay, and that is x1, x2, xp, and each one is a function of t. In the brain imaging, p is 64, 64 many networks in your brain, and over the time t belongs to AV, the brain, the image are moving, and just try to look at it is a vector, each components may have some dependence. Whenever you are considering a random vector in the multivariate normal, don't need to think about even functional data. In the multivariate normal, if sigma is of diagonal elements are non-zero, that means there are some dependent structure. Here also it may have that the x1t, this function will have some dependent structure with the x2t, it is not independent. So essentially what he is trying to say by the brain imaging data, this is you can think about, that is a p-dimensional vector. In the example he considered, that is a 64 dimensional vector, each component itself is a function, okay, and each component may have some dependence. That means location, that means spatial temporal data, that means there is this network and this network has some dependent structure. If you change the location of the network, then it will create a problem. It will not problem, it will give you different structure, different data. Another one is that is called functional time series, where the value at each time point itself is a function. That is slightly complicated to visualize, and spatially and temporally varying curves, images of the brain obtained from an MRI, etc. Possibly he discussed about the MRI. Okay. That picture you are already familiar. You are already familiar with this picture. This is suppose you are writing the FDA, functional data analysis. So that is also handwritten. So handwritten writing. So that one is a functional data. That means you can think about this is a function. Okay, this is a function. So there are say 100 many functions is there, handwriting analysis. Okay, just I want to discuss some mathematical, very basics mathematical fact. I already defined expectation of x. Last day I discussed something about the first day when I discussed the probability theory. I discussed about first I defined the probability, the classical definition of probability, relative frequency definition of probability. Then I defined the modern approach, then I moved to theorem of total probability, first conditional probability, then theorem of total probability, Bayes theorem, then random variable expectation, everything I did one by one, everything we discussed. Now if you look at if you think about what was the definition of expectation of x, in that case, first of all I want to clarify one thing is that for natural functional data, the way I started my lecture, today's lecture, I mentioned that the functional data, the way you can think about, those are all realization from the stochastic process. Instead of a distribution is generating stochastic process like Brownian motion or something like that, then functional data is nothing but the realization of the parent distribution of the stochastic process like Brownian motion. So we have to define properly the expectation, variance, all those terms in the functional variable. So what is expectation? At least I don't think everything will be possible, but just you try to think about what was the definition of expectation. Expectation means integration x dfx or x small fx dx, or you can write, since small fx is the density function, is a differential of the distribution function, you can write x dfx. So here also we can define, suppose f is a function defined on a measured space omega script f mu, who are not from math background don't need to think about. And separable Banach space is a complete normed linear space. Complete means Cauchy sequence converge, and normed means it is associated with it has the norm. And we want to define this integration. We don't need to think about, forget about separable means you can have the orthonormal expansion, that is called, why it is called separable. So we want to define just integration f d mu, that means essentially f omega mu d omega. And who are already familiar that the construction is exactly same as the way we learned at the measure theory Robert has book, that the way we define the f d mu means first we try to define in terms of simple function, then you try to define for the non-negative function, and any function can be written as a positive part difference between two non-negative function, one is f plus and f minus, so you can define the function. So that's the simple idea. The Bochner, in Bochner sense, the integration is the same thing. So one thing is that first of all we have to understand, I just telling the fact, in the case of functional data, whenever I am thinking about the functional space, we don't have any density function. It is still our open problem. To define the density problem, just try to think about, in the univariate case you know what is density function, probability density function. In the multivariate case you know what is your probability density function, meaning of probability density function you know. But in the functional space, in the theoretically you don't have any, there are any density function, concept of density function. Similar concept is still there, but already there, but exact concept of the the density function in the functional space, it is not still available. So that is my integration f omega mu d omega, and the way you can think about a function is called simple if it is can be represented in this way. I is indicator function. Last day I defined indicator function. If omega belongs to ei, that is 1. If omega does not belongs to ei, that is equal to 0. Okay, f omega equal to, for some finite k greater than or equal to 1, they don't need to think about all those things. Ei belongs to, suppose ei taken from the any set, and ci all belongs to script b. Then we can say that the integration f d mu is integrable in the Bochner sense, with the Bochner integral is given by integral f d mu summation over I equal to 1 to n ci mu ei, and that's the definition in the whenever we learned first time measure theory. I don't know three of you know the measure theory or not. That is the typical definition, the way, very basic definition of the integral. If we approximate, if we consider the function is a simple function, that is the definition of the integral. So in that case it is called Bochner sense. There is another concept in the literature is available in the functional space, that is Petit's integration, but that you don't have to think about right now. That is more popular. The Bochner integration is more popular. The same definition. Now this is the fact that if you have two representation, both is the unique, that means that will give you the same thing. Now what is the, when you will call it is a function is Bochner integrable. Bochner integrable if there exists a sequence of simple and Bochner integrable function fn such that this difference equal to 0. In this case Bochner integral of f is defined as integral f d mu limit fn d mu. That means you have to find out the sequence of simple function fn that converts to f. It is, you can think about integration limit, that means fn is uniformly converts to f in L1 sense, then the Bochner integration is nothing but this one. I just want to mention, and I just want to mention these are too technical, but one thing I want to mention that all those dominated convergence theorem, monotone convergence theorem, Fathus lemma, everything, whatever we have learned in for the real valued random variable, everything is possible to here also. That means there are all versions of, just you want to, if you have to, for any reason, if you have to do mathematics for the functional space, Whenever the random elements are belongs to the separable Hilbert space, blindly you can use the Fathus lemma DCT MCT. There is no concept. You cannot use blindly all those problems, all those issues like the compact means closed and bounded, that you cannot use. Definitely those have different meaning. But this Fathus lemma, there are main three results what we have learned in the integral calculus. Fathus lemma, monotone convergence theorem, dominated convergence theorem. These three are the pillar of the integral calculus. So these three pillar is valid here also. That's I am telling you. Then I am just want to give you some idea about the So what I said that at the beginning that the functional space means, you can think about functional data means it is a realization of the stochastic process. So if you want to prove any mathematical problem that this sequence of process converts to a particular process, how do you prove that? That means you know what do I mean by x1 x2 xn is a sequence of random variable that convergence in distribution to x, you know the meaning, exact meaning you know. If it is random vector, you know central limit theorem. In that case your option is that central limit theorem. In the case of random vector, you know Cramer-Wald device, that is essentially multivariate extension of the central limit theorem. In the case of, you don't need to think about this node it is too technical, it is written. Just I am asking intuitively, if you have instead of the x1 x2 xn or x1 curl x2 curl xn curl, suppose my random sample is x1t x2t xnt, t belongs to some ab closed interval. In that case I want to know that sequence of random element. You can think about random element, though that element converges weakly to some other random element xt means, what does it mean? In the one dimensional case, that means that sequence of distribution function will converge to the distribution function at the continuity point of x, that's continuity points of f, that is the definition. But in the sequence of stochastic process, anyone has any idea? If you want to say that converges weakly to some other random element xt, then that means you have to consider there are two issues you have to take care in that case. Just I am telling you, two issues is that, one issue is that if you make an arbitrarily if you take the t belongs to fe, you take arbitrarily many points t1 t2 tk. If a k dimensional vector will converge to the corresponding k dimensional vector, and along with the fact that your sequence of process is bounded in probability, both fact will give you the idea that weak convergence. Okay, what I am trying to say that I think that should be written properly. So CLT for random variable, that you know x1 x2 xn. Cramer-Wald device to prove the weak convergence. Now my problem is little bit more, x1t x2t xnt, that sequence of random element that converges weakly to a xt. Okay, that how do you define, that how do you characterize? So I am saying that in the case of if you face this type of situation, t belongs to ab. So in that case what you will consider? Consider T1, T2, Tk arbitrarily belongs to AB. So instead of the x1 t, xn, x2 t, xn t, consider the corresponding k dimensional vector. That means x1, that is now k, not a function, this is reduced to vector x1 t1 comma x2 t2, x1 t2 comma x1 t3 comma x1 tk, that is k dimensional vector. Next one will be x2 t1, x2 t2, x2 tk, that will be another k dimensional vector. Similarly here also xn t1, xn t2, xn tk, that is also k dimensional vector, and that would converge to, we have to check that whether it is converging to weakly to xt1 comma xt2 comma xtk, that k dimensional vector. Okay. If it happens, then the finite dimensional case is that means we don't have to think about the finite dimensional, but that finite dimensional convergence is not good enough to prove that this type of convergence. In that case you have to prove more that this sequence of random element that is uniformly bounded in probability, that means supremum over t, that means, or you can take supremum over n, supremum over t, probability mod xn curl t get less than or equal to m, that probability will tends to 1 as n tends to infinity. So that's also, that is a technical issue, but just I want to give you an impression that the difficulty level of the functional data or the stochastic process, handling stochastic process, whenever you have random variable or random vector, our tricks are nearly same, more or less same tricks we use. In that, just you try to think about the difference between central limit theorem and Cramer-Wald device. Central limit Cramer-Wald device is essentially the straightforward application of the central limit theorem. Just we are using the fact that definition of the multivariate normal. Now what is multivariate normal? X curl is a random vector which follows multivariate normal if and only L transpose X follow univariate normal. L is arbitrary vector. So that is the definition of multivariate normal. Simple definition. Don't need to think about, don't need to recall the long PDF, all those things. If someone asks you what is multivariate normal, that is the characterization of the multivariate normal, if and only. So Cramer-Wald device is nothing but the direct extension of the central limit theorem using the definition of the multivariate normal. In the case of stochastic process, whenever our random elements are the stochastic process, it is not direct straightforward extension of the central limit theorem. We have to add more. First of all, the arbitrarily finite dimension proof, and second is that uniform boundedness also we have to prove.
So this T1, T2, Tk are some fixed quantities in
arbitrarily points. For a suppose t equal to 0 to 1, you can take 0.1, 0.3, 0.7, 0.9, but k can be arbitrarily, even choices out can be arbitrarily. So it is true for, that means I should say it is true for all T1, T2, Tk. K can be arbitrary, the choices can be arbitrary.
That is how I am taking the randomness part of this.
And moreover, the tightness, whenever I am thinking, the way I generally try to think about why uniformly boundedness we need it. Suppose this is my sample curves, ECG curves. Okay. Now I want to mention that this one is converges to as n tends to infinity, something like this curves. So if we don't have the uniform boundedness, then it may have, suppose our sequence of the random sample, that means random sample of the stochastic process, if they don't have the uniform boundedness, then one curve might be this one, another curve might be this one. So then we cannot control the sample path, essentially the amplitude, that means the zigzagness of the sample path we cannot control if we don't impose the uniform boundedness. So that's why there are two conditions both together we need. One is that for arbitrary choice of T1, T2, Tk, we need the finite dimensional distribution, and uniformly boundedness essentially control the behavior of the, just try to think about the behavior of the sample paths. For example, in the real analysis, you know, sin x is a very nice form, but if you look at the sin 1 by x, that function does not have the fine nice graph. So in that case we lose the uniform continuity even. So that is the idea. So we want to make it everything uniform, that's why we impose the another condition that gives us the CLT. And since already you know little bit about the nonparametric regression, so you can think about nonparametric regression also a problem related to the functional data even for the one dimensional case because m is a function, y equal to mx plus epsilon. Even if x is a real value, m is a function. M belongs to a, what I said last day, m belongs to a infinite dimensional space. It is belongs to a functional space. So whatever we are dealing with the functional space, that means whenever you are dealing with the non-parametric regression, essentially you are dealing with the functional space. And in that case also we have all those estimators like Nadia, Bertson, Grasson, Muller, all those things we need. So there are some definitions just to try to think about. Consider a stochastic process x, xt, t belongs to E. E you can take compact set and define its mean function and covariance kernel in this way, mt equal to expectation of xt and kts equal to covariance xt xs, ts belongs to irrespectively provided they exist. And process with well defined mean function and covariance kernel are called the second order process. Of course, k dot, it is a covariance kernel. You know that a covariance function is a covariance matrix is a positive, non-negative definite matrix. So definitely the kernel, you will have a non-negative definite. A kernel is non-negative definite means if you multiply by ai aj, double sum ai aj, k xi xj, that would be greater than or equal to 0. And this is some definition. So anyone has any idea about the this type of stochastic process? For example, what will be the mean function for the standard Brownian motion on the covariance kernel? If xt is a standard Brownian motion, what is expectation of xt? 0. And covariance of xt xs, that is equal to minimum of t and t comma s. So in that case you can write, and that is non-negative definite, all those things exist. So you can think about Brownian motion is also a second order stochastic process. Second order stochastic process, so whenever you don't have to think about the mean, the covariance exists, that means it is called the second order stochastic process. So Brownian motion is a second order stochastic process. Now we can define all those continuity for the real numbers, for the vector numbers, for the vector value. Do you know what do you mean by the continuity? Here also you can think about that is mean square, one analog of the continuity, that is mean square continuous. If a second order process xt is said to be mean square continuous, if this happens, can anyone relate it with the real analysis result? A second order process xt belongs to t belongs to E is said to be mean square continuous if this happens. So what is the continuity definition of the functional? Function is a sequence of function a function is continuous. How do you define in the real analysis? Sequential definition of the continuity. If x1 x2 xn is a sequence of real number that converts to x naught. If f is continuous, then f of x and that sequence will converge to f x naught. So here also the same definition. We are considering a sequence of number tn. Tn belongs to t, limit expectation of xtn minus xt whole square, that is equal to 0. Okay. Okay. I want to show one result. That is very crucial result. All those mean square, all those concept is you can extend. Now this is possibly the most important result, one of the most important result in the functional data analysis, and that you have learned, that you have done a lot. Suppose xt is a mean square continuous stochastic process with covariance kernel k dot dot, then kts equal to this one, summation over j equal to 1 to n, lambda j phi j t phi j s, where the sum converges absolutely and uniformly on E. Here lambda j and phi j eigenvalue and eigenfunctions of the integral operator on H associated with k dot dot. So this is very technical, it seems very technical, but what is the connection with statistics in this result? This is what they said. This is my covariance kernel. This is a function of t and s. That is called Mercer's theorem. If a process is a L2 process, then covariance kernel sorry, then covariance kernel can be written as in this way, that sum over the orthonormal expansion. This is simple orthonormal expansion, infinite times orthonormal expansion. So what is the connection with the statistics? Any result, any procedure you have learned in statistics? This is essentially spectral decomposition, some sort of spectral decomposition. If you have the, you know that if the, suppose x curl follows, suppose x curl is a multivariate normal distribution. Just I am asking one very related question. Suppose x curl follows multivariate normal distribution with mean vector 0 and variance covariance matrix sigma. Okay, in that case, what will be the distribution of norm x square? How do you prove that? My question is clear. My question is that if how do you prove that? This one. Suppose x curl follows d-dimensional 0 curl sigma matrix. What will be the distribution of norm x square? How do you prove that?
We take a transformation of x multiplied by sigma half inverse. If sigma is known.
Yes, sigma is known. Suppose sigma is known.
Then I can convert it into like, if it is 0, then like each element is.
Mean will be 0 even after converting. Then you will have sigma to the power minus half, x curl will follow normal 0 identity then. But it is not, this is norm x square. Norm x square. My question is clear. I will show that what is the connection between this and that essentially. That spectral decomposition you have to do. X curl follows normal d0 sigma. Sigma is some sort of, sigma is a positive definite matrix in general. I am not considering even non-negative definite matrix. So if there is, if you have one positive definite matrix, then there exists a one orthogonal matrix such that A sigma A equal to diagonal matrix with diagonal elements are the eigenvalues. That result you know. So Ax curl A is that suppose A is that orthogonal matrix which will make the diagonal matrix, which will make it diagonal. So Ax curl follows normal d A into 0 curl into A sigma A transpose. A into 0 curl is 0 curl, and A sigma A transpose is diagonal matrix with lambda d. Now I am taking the norm. Now you know if it is lambda 1, lambda 2, lambda d. So this is the result. If that means they are now my components are independent of each other. Off diagonal elements are 0. Okay. So what we can say? Norm of Ax curl, that whole square will follow lambda 1 square into chi square 1 plus lambda 2 square into chi square 2 plus lambda d square into lambda d into chi square d. These are all variance. Lambda 1, lambda 2, lambda d are variances. Okay. Variance of the first element is lambda 1, variance of the second element is lambda 2, variance of the dth element is lambda d. So that will follow, Ax curl will follow summation over I equal to 1 to d lambda I chi 1 square I, definitely they are independent random variable. These are the random variable related to chi square. Now what is norm Ax square? Norm Ax square, you know, norm x square equal to x transpose x. So that is equal to, you know, the definition of the orthogonal matrix. A is an orthogonal matrix. A transpose equal to A transpose A equal to identity. So this is equal to norm x square. So norm x square will follow the also the this one, this weighted chi-square, this weighted chi-square distribution. The result we are using is that sigma, if sigma is the positive definite matrix, sigma can be written as, that means summation over lambda I. That way we can write essentially KTS. If you write L2 process, if x cal belongs to L2 process, if you take the norm square, that gives in the multivariate normal, this is the special case, definitely this is not functional case. In the multivariate normal it will be finite, summation over j equal to 1 to d, then lambda j into chi square one random variable, that will give you the essentially, that is the orthonormal vector, that is orthonormal vector, and that expansion essentially will give you the counterpart of the chi square one. So that is the connection in the infinite dimensional, that is called the Mercer's theorem. And just I want to give you more. Where is Karun and Loeff? Just I am just telling you. Where is Karun and this is Mercer's theorem, and Karun and Loeff expansion is that possible in that note they didn't mention. Karun and Loeff expansion is that not the double eigenvalue xt equal to summation over lambda I phi t, that one is the Karun and Loeff expansion. Just a minute. Okay, k dot is continuous. Mercer's theorem, the proof that xtn ktn that 2n is L2n. Possibly in this note he didn't mention the Karun and Loeff expansion KTN. Sigma field X is the random element in H. This is some sort of centered stochastic process. I mentioned in the okay, just okay, I'm just writing in that case. So this is called Mercer's theorem, and if you have the Mercer's theorem, that means if you have the, if your covariance kernel have the representation of the Mercer's theorem, then any L2 process, that means whenever the covariance kernel exists, then xt can be written if x belongs to L2, then it can be written as a summation over I equal to 1 to n lambda I EIT in terms of distribution. So in that case you can think about integration xt minus this one whole square, the underlying distribution, that whole square, that tends to 0. That's what I am trying to say, that is L2 sense. So in distribution I better to write in L2 sense. If you have the, okay, so that means integration xt minus summation over I equal to 1. Sorry, d mu t as or some say as k tends to infinity. That's why it can happen. The beauty of this, the significance of this Karun and Loeff expansion, what can be? So I am just saying that So suppose a random element has that Mercer's expansion. That means covariance kernel can be written as the orthonormal expansion. That means summation over I equal to 1 to n lambda EIT EJS. Now if that Mercer's theorem holds, possibly that note also has that result, but somehow I am not finding it. That xt can be written as this expansion it validates. That means that is called the Carhon and Loeb expansion. Summation over I equal to 1 to infinity lambda I EIT. EITs are the orthonormal functions. That means integration EIT EJT is equal to 0 and EIT that is equal to 1, and lambda is are the system of the eigenvalues. If xt is in L2 sense this is 1, that means I am saying that the integration, if you take k finite sum, then that tends to 0 as n k tends to infinity. So how do you use this one? That also very well known result you use always in statistics in one particular procedure. So is it not principal component analysis? The same thing you are doing. Same thing you are doing essentially. Whenever you have in the case of finite dimensional, generally we don't do principal component analysis, but infinite dimensional, and that's why we need the separable space. Separable Banach space, I started with the separable Banach space because we have this type of expansion. So whenever we have this type of expansion, what we will do? We don't need to consider the infinitely many terms. We'll in numerical, whenever we will do the numerical calculation, we'll take the a large number of coefficients till say k equal to 500, and then take the multivariate analysis. What we will do? So just to go back to the basic idea, I am just saying that what I wanted to say, that it should be conveyed very properly. Two ways you can deal the functional data. One way is that what I said, xt for a fixed omega, this is a function. You will just take the grid points. You will just take the grid points t1, t2, t100, and to observe those grid points. The function don't need to observe the function in the continuous interval a to b. You just observed in the arbitrarily many thousand many points, and that thousand many vectors you use. Anyway, that has some mathematical drawback. One should not be, but one way, other way, that is one way. Other way, what you can do? Suppose your your random element has this expansion. Okay, instead of taking the whole function, what you will take? You will just have this expansion. Suppose if you know the distribution, you can calculate. Even for the Brownian motion, you can calculate it. So what is your lambda? All those things you can calculate. So instead of taking the whole interval, that means a to b, xt belongs to t belongs to ab whole interval, you don't need to think about that one. You will just take the first principal components. So that first principal components, that means first coefficient c1, c2, c3, c4, c5, and most of the cases in real analysis cases, in the practical cases, you will see that after 5 to 7, most of the lambda 6 or 7 onwards, everything is 0. So very close to 0, I should not say the 0, very close to 0. So we will work with those elements whose are significantly differ from the 0. That is also another tricks to use the in functional data analysis, that you don't have to think about the whole, that means the xt t belongs to ab, you will just consider the first few elements of the principal components, and that will give you the idea. That means you can deal with the multivariate ones. So that is also one of the concept related to the smoothing. It is that time. Okay, I want to say something about the law of large number. So is it clear? So there are 2 or 3 steps I want to say very precisely. One thing is that number one, you have to understand what do you mean by the weak convergence in the functional space. This part is very crucial. In the case of stochastic process, how to prove the weak convergence. In the case of univariate case or the multivariate case, we have the direct result, but for the stochastic process, I don't want to go into that details, that C01 space, D01 space, that will make life more complicated. But just try to realize that it is something different. It is something different from the usual Euclidean space. That means you have to prove the finite dimensional convergence as well as you have to prove the uniform continuity. That means, sorry, uniform boundedness. That is one of the issue. Number two issue is that that is related to the principal component analysis. Just try to understand the skeleton of this lecture. So another issue is that what I am trying to say, that you don't have to think about the whole space T belongs to AB interval. Don't need to think about that. One way you can make the smoothing is that you will make the grid points T1, T2, T100, T500, then observe those points. But definitely that is not choice of grid points, all those issues involved, and definitely you cannot fix the T1, T2, T50. You have to have the arbitrariness of the choice of the grid points. Those issues are involved. But one way you can do that, the mathematical result I stated, that if your covariance kernel has the Mercer's expansion, that means the way I have written that the KST equal to summation over I equal to 1 to infinity lambda I EIT EJS, in the last slide I wrote. So in that, if your covariance kernel has that expansion, in other words, what I am trying to say, that if your random element belongs to a L2 space, that means your covariance kernel exists. In that case, if X belongs to L2 space, then that random element has Carhonen-Loeb expansion, and that Carhonen-Loeb expansion will give you the idea, the orthonormal expansion. So don't need to choose the all coefficients. You will choose those coefficients which coefficients are significantly differ from the 0. In that case, there is an issue that how to choose that, whether that is significantly 0, 0.5 you will consider, or 1.7 you will consider as a significantly differ from 0. That depends on the practice related to the problem, which problem you are dealing. But if it is significant from the 0, then you will consider those functions only. That means only those functions which are associated with this 5 or 7 main functions which are really associated to the 5 or 7 first few coefficients. So that is related to the Carhonen-Loeb expansion. Now I want to say something about the law of large number, about the x and t. They have written x and t has some x minus m equal to summation over x minus y almost surely. Now this is I think that we have to use always in practice. If x1, x2, xn are the 0 mean, then 0 mean is also very crucial. 0 mean in the sense I am saying that the mean is also very crucial. That you have know that in the case of what I said at the beginning of the lecture, that means whenever you are dealing with the random element, infinite dimensional space, your integral is not unique like what we learned in the random variable or the vector valued case. It can be Bochner integration. There is another concept that is Petty's integration, but here the result we are stating that is related to the Bochner integration. That means if x1, x2, xn be 0 means expectation of x equal to 0, and the expectation in the sense of Bochner sense, and pairwise independent random elements in a separable Hilbert space H. Hilbert space means norm exists, inner product we have. So expectation of norm xi square less than finite for all I. Then expectation of Sn square equal to, you can write, is the sum. So essentially the way I can think about the strong law of large number IID case, let x1, x2, xn be a sequence of pairwise independent and identically distributed random variables in H. If first order moment is finite, then average will converge to expectation of x1. That essentially we have learned also in the original case also. And weak convergence, the way they have defined that definition you know also. In weak convergence, how do you define in the case of real random variable? The characterization of the convergence, the way we define. Sorry?
For every continuous function,
If
the integral converges to
integral converts to the f of x, and that integral d mu converts to integral fx d mu. Here also the same definition. Here also you can define the Bochner integration, and we say that that is converges weakly to a nu n is a sequence of random this sequence of distribution. You can think about weak convergence that converges weakly to a nu if fx nu n dx converts to integration fx nu dx. Definitely that integration, definitely you have to, this is Bochner's sense. And about the how to define the normal distribution, Gaussian distribution in the Hilbert space. Anyone has any idea? Stat group, how to define the normal distribution? You know the Gaussian distribution in univariate case, you know the PDF. So, how do you define the Gaussian distribution in the multivariate case? The direct analog, anyone doesn't, anything is not coming in mind? If you want to define the Gaussian distribution in Hilbert space, in Banach space it may be difficult, but in Hilbert space it is very straightforward definition you should have. And that is the definition in fact. So start with the univariate case. Anyway, suppose x is a random variable that related to that associated with the normal distribution. What is that? That we know. That we know. If x is a random vector that follows multivariate normal distribution, that we also we know. If and only if L transpose x belongs to L transpose x will follow univariate normal distribution for every L. So in the case of Hilbert space, you define the same way. So don't need to think about any sequence of any sequence of, that means any arbitrarily choice of function belongs to Hilbert space. The inner product x comma f that follows univariate normal distribution. Is it clear? So just try to think about the way I generally think about what is the multivariate. Whenever we are defining, we know from the when we did the schooling in the primary level, we learned the how to multiply two numbers. Then when you move to the at the higher secondary level, we tried to learn the multiplication between two vector. What is that? That is dot product. X curl y curl, x curl dot product y curl is x1 y1 plus x2 y2 dot xn yn. Now in the Hilbert space, or the Hilbert space means complete inner product space. But if you consider the inner product space or complete inner product space, what should be the analog of the multiplication? That is just simply inner product. That means the way we defined integration, the inner product a comma b, if it is a integration a b, in that way the way we define inner product. So whenever we are defining the Gaussian distribution in the multivariate case, we are moving from one random variable to inner product with a arbitrary vector with the random vector. Now we are moving to one step more, that is in the Hilbert space. We can take a arbitrary function from the Hilbert space. Instead of the dot product, I will consider the inner product. So x comma f, that inner product will follow univariate normal distribution. X inner product f, that is a univariate random variable, that is a scalar value. That scalar valued random variable will follow typical univariate normal distribution. Then we say that if it is true for all f belongs to Hilbert space, then we say that x is a random element that associated with the Gaussian distribution in the Hilbert space. Definitely in the infinite dimensional space, you have to define the mean function and covariance kernel. We don't have covariance matrix or something like that. For example, in the Brownian motion, there is no concept of matrix. It is a function. The KST itself a function of two variable and mean is a function of one variable, and that you know. Just this is very much mathematical. Just I want to say that mean function means what do you think about that? How to visualize the mean function? If you have a stochastic process, the realization of the stochastic process, how do you visualize the mean function? Suppose you have the way I generally think the infinite dimensional or the functional data, that means I have the element from the stochastic process. So I have for a fixed omega, I have say 100 curves. So 100 ECG curves of 100 people, that is my data. So how do you compute the mean from based on this 100 data? So you will just component wise, that means you can take the T1, T2, Tn, T100. Anyway, at least there are functions, lot of functions. This non-white colored curve is you can think about mean function of all those curves. So that way also we can define mean, the average of all those functions. Average means I am saying the component wise average. And how to define the median? Just since the stochastic process, we are dealing with the stochastic process, we may have to try to think about the basic descriptive statistics, how do you define. So mean is very easy, mean is some sort of average of all those curves, but how do you define the median? Median of all those white curves, forget these curves. So is it clear, all of you know mean, median, mode? I believe that. Mode you don't have to think about, because mode is related to the density function, and infinite dimensional space we don't know what is density function. So mode you don't have to think about, but at least median we can little bit think about. Mean is quite straightforward, but median how do you define? If you have 100 many curves, how do you define median? So how do you define median usual for a random variable case, just a real valued random variable?
Probability x less than that particular quantity equal to point we take continuous.
No, but in that case you are x less than or equal to particular point, means you are saying about the, for a given data, that means the way you calculate, you order the data and then middlemost. That is simple. If you have the 5 numbers, you order the 5 numbers, then you pick up the middlemost, that is median. From the multivariate even, ordering is not so easy. Ordering is not unique. That there are several techniques and available, like data depth, all those things. That is nearly ended topic. That is finished topic in research area nowadays. Data depth, all those concepts. Now in the functional space, how do you order? That means you have to somehow order the function. Median means middlemost. Somehow you have to order the function. Now how do you order the function? That is one of the way you can think about. That is one way of approaching the median in the functional space. Another way you can think about, that is more mathematical. You know median at the BSc first year, you have learned it. Who are from stat background, I believe that all of you at least might be a master degree level, you have learned it. You have a number of observations x1, x2, xn. What Professor Maiti discussed so far for a lot of time, he mentioned that the mean means average. We don't know anything, but we know how to average. And average is related to the least square estimator. Average means least square estimator, just what he said again and again. Regression means slightly more than. Mean regression means the usual least square regression means what he said again and again. That is essentially mean regression. We are doing mean is more than one component. So in the case of median, in the least square means what is least square estimator? This is minimizer of the L2 norm minimization, yi minus beta naught minus what he wrote today, yi minus beta naught minus beta 1x whole square without the constant. Lasso or ridge regression, he wrote some constant. Without that constant, that is the least square estimator. So instead of the square, if we take the mod, only mod, that will give you the median analog. Because you know, at the BSc first year you have learned it. Median minimizes the absolute distances from the observations from the median. So median is nothing but the minimizer of the L1 norm of the yi and theta, if theta is the median. Suppose I have the observations y1, y2, yn, theta is my median. That means theta is the minimizer of the L1 norm distance from the yi's. Typical you have learned at the BSc first year. L1 norm you can define in the multivariate case also. In fact, I should not say L1 norm. In the univariate case, this is absolute, just absolute value. In the multivariate case, you can think about this is L1 norm. Here also we can define in the functional space, if you can define somehow the all those things, that means up to Hilbert space you can define the norm. You can define the norm. If you can define the norm, then you should be able to define the median as well. So that's why you can define the mathematically. I don't know whether it is possible or not. Mathematically, you can define the median, quantile, everything you can define. So one thing you can do theoretically for the functional data, you don't need to think about right now the network data, even that functional time series, what I discussed about the network data. You don't need to think about the network data. Simple stochastic process. Data is coming from simple stochastic process. In those data, just try to develop your own descriptive statistics. How to define mean, how to define median, how to define quantile, how to define interquartile range, how to define trimmed mean, how to define all those testing of hypothesis slightly. Just move on just step by step. First try to do for stochastic process, then try to do for say network data. You don't need to think about. I am just telling you, for even network data, I know that a little bit, just a slight, even the t-test type of test, if you can do very carefully, that will be a good publishable work for network data. So even descriptive statistics is not very clear to us for this type of data object. So even defining and their investigation will give you the very good work. That's what I am trying to. I myself also trying to do that. That for stochastic process, when data is generated from stochastic process or network, in that case, how to develop the whole descriptive statistics or inference. You can think about that. Estimation, testing of. To me, inference means three topics: estimation, testing of hypothesis, confidence interval. Or you can think about confidence interval and testing of hypothesis. You can merge. So develop all those basic inferential technique what we learned at the BSc first year. Mu test, t test, sigma test, jet test, all those tests. Just develop for this data. You will face a lot of problem. I am just telling you will face a lot of problem. Not so easy. So we can try to do that. So I think this is the very basics of the functional analysis. So functional data analysis. I will send you the note, because one of the very crucial concept in functional data analysis is reproducing kernel Hilbert space. But that itself will take one workshop. That might be 5 workshops. It may take to cover everything of the functional data analysis. The reproducing kernel Hilbert space. But just I wanted to give you some insight that the difficulty what we face in proving the functional data whenever you are dealing with the functional data, particularly that uniformly boundedness proof is very difficult. That C01 space or D01 space, that proof is not so straightforward. You have to deal with the very difficult advanced mathematics. Next level is that law of large number, central limit theorem. What will be the central limit theorem for the Hilbert space? Till Hilbert space it is okay. After Hilbert space what will happen? And then further issues like how to define the descriptive statistics, testing of hypothesis. Okay, I think I should stop here. Okay.
Simple exercise is that you have 2 curves, test that curve 1 equal to curve 2.
Yes, that is the simplest example.
That's the simplest example I can think of. Like the way you do mu1 equal to mu2.
Yes.
You have the 2 curves.
Prove that 2 curves, that means the generated first curve is generated from some distribution f, second curve is generated from G. I think what I am saying, that is more difficult. F equal to G against F not equal to G. You are trying to say simpler than this.
How?
2 set of curves or 2 curves?
Just 2 curves. How do they do that?
Okay. So in that case, my understanding is that you have to, one way approach is that my experience is that you have to define the distance properly. Distance between 2 functions you have to define properly, then you can develop everything, or that is one of the way, that way you can think about. This is completely open issue, so we can discuss more about that one. Just I wanted to give some highlight. I wanted to highlight that even at the basic level we have a lot of difficulties in the mathematical part, in the theoretical part. So that difficulties, if we can overcome, then we can develop the statistical theory. Okay, so there will be break right now. So then in that case, after that we will come back.